Thanks, Noor and Arman, for the invite. I'm happy to be here and share some of my insights. It's a general talk that will mostly focus on my research and also some of my colleagues' research that I have been closely involved with. And I guess all of us are familiar with these topics. So we have seen deep learning for medical image analysis being deployed in several aspects of analysis, be it classification, segmentation, registration, synthesis, anomaly detection, or so on. The list is very non-exhaustive. We cannot now keep track that what are the things that it has been deployed for. So this, on the left-hand side, is a variety of medical images, and on the right-hand side are some objective tasks that you see here. And the bridge between these two to be done automatically is taken care by this deep learning methods. Some of these are highlighted over here, identifying mammogram mass classification in case of breast mammography, identifying lesions in a brain in case of MRI, or detecting breast cancer metastasis are some of these examples that we see around. But the fundamental question is, why don't we see them being integrated into clinical workflows? What happens in between that on paper we see such great accuracies and such great performances of deep learning model, but their integration fails into the clinical deployment. What is the bridge, or what is missing? And from my point of view, one of the missing piece of puzzle is this deep learning model acting as black boxes. We don't know what goes under the hood that these decisions are being made. We simply have some input and we have some output and we just measure the accuracy, but we seldom or very often we don't go into understanding the mechanics behind what is going on in case of these decision-making processes. And to support myself, I have two pictures that were taken at different McKays. On the left-hand side, you can see that a challenge to radiologists embracing AI in practice is we don't really understand how it arrives at a conclusion. And even in McKay 2023, it was pointed out that there is a need to open this black box up. So over the course of next few minutes or so, I'll be talking about several works that we have done very recently that focuses on this topic of opening the black box and solving the problem of explainability. And we have been successful in establishing some of the benchmarks in the field of explainability, and especially through foundation models that we have seen around. So let's jump right into it. The first work that I'm going to talk about is PRISM. It was runner-up for the best overall paper at McGill, which was in July 2025. It's called High Resolution and Precise Counterfactual Medical Image Generation Using Language-Guided Stable Diffusion, which was done in collaboration with my colleague Anita Chris and our research collaborator, Mohammad Hawaii at Google Research, and Professor Arbel is my supervisor. So this medical AI crisis that deep learning models are not reliable in medical imaging tasks. If we drill down further, what are the issues that we see? The first issue that we come across is spurious correlation. And if you're not familiar with this, this can simply be understood in terms of shortcut learning, which is that while doing this medical analysis, it's possible that the model achieves very high performance. But instead of looking at the underlying disease, it's latching onto something that it should not latch. So essentially finding shortcuts in order to satisfy the objective function that is given. And this spurious correlation becomes a huge problem that essentially hampers model deployment. And one of the popular use case was during COVID-19, when they deployed several models within a clinic. They were able to detect COVID-19 from the chest X-rays, but when they actually tried to generalize it across several hospitals, the model failed to generalize. And the main reason was that it was looking at some of these artifacts that were generated from the hospital. So essentially, that those are spurious correlations. The second is data imbalance. I guess I don't need to share more information about this because very often in case of medical image analysis, we see underrepresented classes. We don't have enough data that represents overall population or overall subgroups, and that leads to biased predictions of the model. And finally, these lack of transparency are not interpretable or verifiable by clinicians. So essentially, what we are saying is we cannot just give the final result to the clinician and say that, oh, the model was this percent accurate. How about deploying them in clinic? That will be catastrophic in case of deployment. And finally, there are very limited annotations that is available for medical data set. Also, I'm talking about digital annotations rather than some of the marks that are made across some of the hospitals. But to digitize them and to collate them is also a challenging problem. So essentially, if we treat this clinical scenario, we have a medical image coming in and our deep learning model, which is essentially a black box. And the diagnosis for this clinical image is pleural effusion. As a human, the fundamental question that we'll ask is this model correct? If yes, is it correct because of correct reason, which is essentially, is it right for right reasons or right for wrong reasons? Which means that just the decision is correct, but the reasons are wrong. And finally, is this a generalized diagnosis which is satisfying the overall population, or is it like a personalized disease diagnosis that the model is doing, which is very much related to only this specific person and not a generalized population? So this is where our approach that we pitched comes in. The traditional methods in this case, I guess you're familiar with some of these methods such as LIME, SHAP, or GradCam, which is post hoc based explanation methods where a classifier is trained. And then these methods essentially exploits the gradient and highlights the region of image that is responsible for making those decisions. But it's not a great way, mainly because all you see is big blobs that are highlighted and not exactly what disease pathology are we looking at. There was some work that was also done in the context of AttriNet and GIFsplanation, which are latent space-based methods. If you're interested, the reference is mentioned at the bottom. But in summary, what they do is they look at the latent space, they perturb the latent space slightly, and then end up creating more images or more explanations of the same image to show that if this particular thing was not there, this would have happened. And then these latent space, when passed through the decoder, are able to create a whole image, and then essentially the explanation is looked at. What our approach is that ask this question: what minimal change should be done in image such that it alters the outcome? And on this basis, we had also a previous work that was an oral at middle. It was called Decodex, which was classifier guided diffusion based explanation, where we showed that diffusion methods could be combined with any black box model, any off the shelf classifier, and these diffusion models could exploit the decision making process of a classifier to explain what is going under the hood. But I'm not going into details of that work. What's more interesting is the solution to all this comes from the generative model. If you have a high capacity generative model, you will be able to explain it in a much better fashion that what is the model exactly looking at while making the decision process. To talk about this more concretely, what am I referring to is explainability via counterfactual image. So imagine that original image, which is shown on the very left-hand side of this picture, and it's given that the person is sick. We ask this question that what would this person look like if it were healthy? So asking this what if kind of question, which is essentially counterfactual explanations, and then we use this high capacity generative model to synthesize the counterfactual image, which is shown in the center. So this is essentially synthesized, the central image is synthesized by our model. And once you take a difference map of the two, you can see a very clean explanation of why the patient was sick. In this case, the patient had cardiomegaly, which is abnormal enlargement of heart. So to look into explanation a bit more, I'm just trying to see if I can grab my cursor here. I think this should be visible. Yes. So heart is located in human over here in the central region. So if there is an abnormal enlargement, you can see that this region is enlarged. But if this patient were healthy, this enlargement should not be there, which is shown over here. And a difference map of the two is clearly able to show that these regions should be there had the person been healthy. So essentially, the goal of this counterfactual generation, which is an answer to the question that we asked at the top, that what would this person look like if they were healthy, is that it should follow minimal changes such that it should not change the whole patient at all. And the generative model just copies an image of a healthy patient. That's not an optimal solution. It belongs to the correct target class, which means that it should be healthy and it should show realistic changes. There are another ways in which you can satisfy the above two condition, which is essentially by just performing an adversarial attack in which the changes are not meaningful or clinically relevant. Still, the decision process can be changed. So if we follow these three restrictions, which is showing minimal change, belonging to the correct target class, and showing realistically and clinically relevant changes, we essentially end up with this counterfactual image in the center. And the difference map is an explainability map, which clearly highlights the region instead of showing a big blob. So imagine if a grad cam was done on top of this, you'd get a big blob in the center, but not know exactly what changes was needed. So that's the advantage of having counterfactual explanations over any traditional methods that are available out there. So where does foundation model comes into picture in all of these? The foundation model acts as a new paradigm for bringing in high capacity models because these images are extremely high resolution, and we were also one of the first to generate these images in the context of chest X-ray that we were able to synthesize high fidelity images at 512 cross 512 resolution. And what was important and interesting about this work was it was able to have precise control over the image using just text description. And what's also interesting is that we never showed to the model that what this text is associated with, which essentially leads to the last point of the contribution was we were able to perform semantic understanding using massive pre-training from diverse data set, and this was on natural corpus. So we are not even utilizing the entire image-based corpus information. Rather, we are taking the pre-trained language model that was trained on natural languages, not medical images, and still utilize them for medical imaging tasks. So what did we do under the hood over here? We took the pre-trained stable diffusion 1.5 model as the backbone for our architecture, and we utilized the pre-trained image encoder, which has a rich visual understanding of generalized images and is also very good in robust feature extraction. So we don't change the image encoder. And we also use the pre-trained clip encoder, which is trained on millions of corpus of natural text. So these texts are like painting of flower in vase, photo of sunset, utilizing that for just two simple tasks, which is that it should be able to understand the language. In this, we are referring to only English, and also perform image text alignment. Once we have these two, we just fine tune the generative component. So if you're familiar a bit about with stable diffusion, which I'll go to in the next few slides, we fine-tune the unit component of the stable diffusion to make sure that the generative process understands what does medical image refer to, and in the context of medical image, what can these natural language changes bring into the image. So all this fine-tuning was done to understand medical domain knowledge. It understands clinical relevance. There is also anatomical precision, and it also understands pathology. So let's look into the architecture in a bit more detail. So this architecture is same as the original stable diffusion. We have the image encoder and we have the clip text encoder. This clip text encoder takes natural language into input. In this case, we have chest X-ray of a patient with lots of medical device. Notice that these two encoders are frozen. So that's the beauty of the model. We are not modifying a lot of things. It's an image encoder that is trained on natural images, still has a very good and rich representation of medical image. What we change is this central part of the of the stable diffusion, which is where the cross attention happens, and this text information is combined with the unit components, and there are several of these units cascaded in a usual diffusion process. And we use denoising diffusion inversion process over here, DDIMs, to make sure that the mapping is bijective, which essentially means that instead of doing a probabilistic sampling, we are doing a more deterministic sampling while synthesizing a counterfactual image. So this central part of the unit, which is this region, is essentially fine-tuned, and this fine-tuning happens with this text, which is generated more from a template. So essentially what we have is we have a table which shows that disease is present or not present, and multiple of these diseases could be present at the same time. We just convert it into template text, and then we have image. So we create this image text pair to fine tune just the unit component of this stable diffusion architecture. And what we get from here is, if we look at the null text inversion, which is essentially after this fine tuning is done, just pass it through the same decoder of the stable diffusion, you can see that the inverted image, which is essentially created from the latent space, is almost similar to the original image. What this ensures is, while this inversion happens, there is no loss of information. So this is what affirms that our model is actually a high capacity model. If it was not, we would see a lot of distortions over here, which is essentially not the case. So the aim was not to obtain the inverted image, but the aim was to obtain a counterfactual image, which you can see over here. Now, if you compare this counterfactual image with the original image over here, the edit text was also provided, that chest X-ray of a patient without medical device, which is highlighted in the green. So just this difference, which is with lots of medical device and without medical device, understanding that semantic context, it's able to erase these medical device. In this case, you have a pacemaker and you have a lot of chest tubes going on. Those are completely erased from the image like a magic tool. So this is what the model was capable of doing. Uh, there is something more under the hood rather than just fine-tuning the stable diffusion, which is essentially looking at, give me a second, over here. So we have a clip semantic score, which is essentially similar to cosine similarity. We take the difference in image editing, which means that we pass the original image through the image encoder, and we pass the edited image through the image encoder, which is the counterfactual image, and we take a difference of the two. And similarly, we also take a difference with the text embedding, which is passing the text, the original text and the edit text through the image encoder. And we do a quality filtering, which is if this clip similarity score is less than 0.1, these samples are filtered out. This is an established threshold from the field, which people have observed in the natural language domain. So performing this clip similarity on top of the editing that was just now explained in case of stable diffusion is allowing us to have this control over image editing process. So what do we get after doing all this? We get a vision language foundation model, which can perform free-form image generation. What does that mean? You can simply give it text and it's able to synthesize image. And we have also established that these images that are synthesized are actually meaningful. So over here, you can see that it was given chest X-ray of a patient with severe cardiomegaly and a lot of support devices. So it generates pacemakers, wires, a couple of stitches in the central area, and the disease is also present there. On top of that, we are able to perform selective attribute control, which means that we are able to modify specific features while preserving the others. Here is another example where you can see that chest X-ray of a patient with lots of medical device on the left-hand side, and on the right-hand side, it's just erased. So this vision language foundation model acts as an eraser, which essentially removes all these medical devices in one go. And finally, it's able to provide counterfactual image synthesis, which is essential for explainability. So if we look at a few more examples, that how is it able to remove these devices, you can see a comparison with a GAN-based approach, which is also at lower resolution. It's almost at half resolution, 224 cross 224, which was previous state-of-the-art GAN-based method. And still it's unable to do these tasks of removing these fine-grained medical devices. However, here, which is our approach, you can see that these are removed just in one shot. Now, to give a bit more context about this, the removal of these medical devices is not easy because these devices could be anywhere. The location is not specified. We are not providing any mask or size of these devices. It's just based on the semantic understanding that there are some devices present in the image, find them and remove them. Doing such a task without any extra supervision is a very difficult process, and any of the methods that exist out there is limited to perform this at high resolution, and also the downstream performance that you get is not good. Second, about explainability of the disease. This is actually an animation, so you can take a closer look at this. Just observe or stare at this animation. The initial start point is chest X-ray of a patient with cardiomegaly, which is again abnormal enlargement of heart. And the edit text that was given was chest X-ray of a patient with no findings. So essentially asking again the question, what if this patient did not have any disease? And you can see that in this animation, it's able to ignore all the other areas, including the necklace that this patient might be wearing, and focus mostly on the region that targets the heart. And you can see that the method is able to suggest that if these lung area were not enlarged as much as it is, this patient is actually be healthy. It not only explains cardiomegaly, but a lot of other devices, which is referred in the paper, like pleural effusion, which is shown over here. So another set of examples where you can see that the original image of a patient, which actually has pleural effusion, which refers to the costophrenic angle of the lung. These corner of the lung is destroyed when the patient has pleural effusion. And in the counterfactual image, you can see that it was suggested that if those were created, this patient would actually not be sick. What's interesting is this approach also ignores confounder. So this is what we were talking about in the beginning, that a lot of time model just latches onto spurious correlation. And in literature, there is a lot of reference that is available, which shows that pleural effusion is associated with these devices that we see, and a lot of time these devices actually cover the region that is at the costophrenic angle of the lung. So to have a model which actually ignores these confounding and focus on the disease was the contribution that we made. Apart from visual changes that we see over here, this could also be used to improve the downstream performance of classifiers. So what we did was we took the original data, which is readily available, the same data that was used to train this model. We see the performance, the downstream classification performance across 4 different diseases. What we did was we simply augmented them with counterfactuals that we synthesized using this method. And simply augmenting and observing the performance increment actually showed that we were able to slightly improve the performance in some cases. And in case of pleural effusion, which is confounded with medical devices, we are actually able to improve the downstream performances quite a bit. So this method Prism, it was able to synthesize images that were actually helpful in improving the downstream performances of classifier. To complete the story, how does this compare with any other image editing method that actually exists out there? So Radit is what was developed by Microsoft. Imagic is developed by Google, and null text inversion was one of the very early stage image editing method on top of which Imagic was also, I guess, built. So you can see the comparison on the same image when we are able to edit these wires or this tube that can be seen in the lung. And across other methods, some of these methods actually damage the image itself and even hallucinate by creating new devices, as you can see in these bounding boxes areas. And you can see that our method is able to finely edit them with very high precision, and it outperforms all the state-of-art methods that actually can remove these devices. So in summary, this approach was successfully adapted to address critical biases because these confounding variables or these extra medical devices that we see actually create biases in the downstream diagnosis of several of these tasks. These VLM was able to create high resolution and high fidelity image. We also showed in the paper that they could be used to build robust classifiers, robust to confounding factors, robust to even disease classification. And we also showed that this worked on different modality skin images. For the purpose of time, I have ignored skin images, but it's also available there in the paper. So if you're interested, do check it out. But does the method stops here? Not precisely. So we have a couple of follow-up works in 2025 itself at CVPR workshops and a McGill main track conference as well, where we showed that the same method of fine-tuning these foundation model could be used for several other tasks. And I'll go through some of these tasks quite rapidly. So let's look at some of the works that will be presented at MICAI. It was mostly done by Parham, my colleague, and Mohammed Zara and my supervisor Tal. So this method, what we talk about is called RL format DDPO. It's a reinforcement learning based framework where we showed that foundation models can be leveraged to create diverse medical images. What do we mean by that? So in Prism, we showed that when we give it a language-based instruction, it's able to synthesize image, which is good. This image could be used for addressing the confounding factors or could be used for addressing downstream classification. But what's interesting is that these foundation model also starts learning biases. What do we mean by that? When we give it a text prompt, it does what it's supposed to do, but it does a bit more extra. For example, in this case, we gave it that generate skin images of patient with melanoma. It does that, but it also creates these artifacts, which is rulers that is shown in the red boxes. What we wanted was that these images better align with the text prompt that we are giving. So essentially, image text pair alignment was the issue. And we showed that if this issue was addressed, we would even further develop our model for performing better while doing downstream tasks. So essentially, the objective is very simple. Just remove this unwanted but relevant artifact that actually don't align with the text prompt. So what we did over here, if we look at the network architecture, we simply added a reward-based function. So we borrowed this idea from reinforcement learning, and I guess it is also one of the first frameworks that is proposed for having reinforcement learning in medical imaging, where we are improving the performance of image generation. And the secret sauce lies in this right-hand side, which is the reward function. The left-hand side is the same architecture that I explained in the context of Prism and chest X-rays. On the right-hand side, what we have is a multi-head attribute classifier. This classifier is taken off the shelf. It's not trained with the network. And it has also seen the exact same number of samples that this entire network has seen while fine tuning. So we are not passing any extra information to this. But what this multi-head classifier is able to do, it's able to identify artifacts as well as disease in this image. So for example, given this image, the highlighted region shows what are the things that are present in this image. There is hair, and the disease in this case is melanoma. So once those artifacts and those attributes are identified, we actually have a policy gradient update similar to a reinforcement learning based fashion. And this actually even further fine tunes the stable diffusion, and done recurrently, this does better image text alignment. So how does this architecture help? In this case over here, on the very left-hand side, you have real samples that are shown. On the center of this slide, you can see synthetic image, which are generated by fine-tuned stable diffusion. So this stable diffusion is similar to what was trained for Prism, but you can see this extra artifacts that are being generated, ruler, ink, or some of the extra patches that we essentially don't need. And after doing this realignment, we are able to improve this downstream performance, that these extra set of artifacts are no more available. So essentially, what we are able to claim is that the model is no more hallucinating. How does this architecture help? This actually helps for disease diagnosis. So in the context of numbers, we have shown in the paper, which is also available on archive. And I'll share these slides so you can take a look at these in detail if you're interested. But these architectures actually helped with the downstream classification of several of these diseases. So what we did was we did a baseline comparison of the images that are completely synthetic image that were generated from the fine-tuned method, and the architecture that took into account this reinforcement learning based method. And once we had these synthesized images, we were able to repopulate the original data set, and we showed that it improved the downstream classification task. And if you are think about it a bit more, what we are able to do with these approaches is that we are able to synthesize combinations of those images that do not have a good representation in the original data set. For example, some of the combinations with disease with a particular artifact had just 4 real samples. We actually populated them because now we have the liberty to generate these high resolution image to actually show that once these underrepresented classes are populated, you can actually address the bias in the downstream classification process that happens. So that was one line of work. The other line of work, which was done with Zara and supervised by Tal, was called language guided trajectory traversal for disentangled stable diffusion latent space for factorized medical image generation. So this is also something very close to what we talked about right now. So in case of Prism, we were able to do a single point edit. We showed that using language, we are able to remove certain artifact, or we are able to control certain artifact. What if we want to have a continuous trajectory that we constantly control a particular attribute, which could be disease, which could be artifact? So here is a intuition behind this work. So we have a start point, which is a synthetic image that is generated using this foundation model that I just explained. And we have 2 different trajectory. One trajectory refers to disease, which is pleural effusion in this case, and the other trajectory refers to medical device. What we want is, as we move along this trajectory, we should be able to control the attribute that we want. So essentially what we are trying to do here is make sure that along each of these trajectories, we should be able to modify some of these artifacts. The way this was done is shown over here. So in this fine-tuning process that I just explained, what we did was we removed the cross attention that was being supplied from the encoded image representation. So in case of Prism, the encoded image representation, sorry, encoded text representation stayed same throughout the whole denoising process. But what we are doing here is, for any given time t, we keep the encoded text representation same, and then we swap it out with the new style embedding that we want. And essentially, this creates interesting results, as you can see over here, is with using combination of same styles, such as chest x-ray with no significant finding, from chest x-ray showing pleural effusion to chest x-ray showing support devices, the 2 different trajectories. And as these neural embeddings are swapped, we see that we obtain different variations in the image that is controllable. To understand this a bit more effectively, it can be seen as this process. So imagine a denoising diffusion process that happens from t equal to 0 to t equal to capital T. And if you swap out the neural text embedding at time t equal to capital T, you end up with a completely different image. But what if you do denoising diffusion for some step with neutral embedding and then swap it out somewhere in the center? What you end up with is this controllability over the images that we showed in this paper. And essentially, what we were able to discover is that the latent space of these foundation models are very rich, and they are able to show disentangled properties across each of these dimensions. As shown over here in t-SNE plot, we can see that the same neutral embedding point, which or the start point, is shown by this black dot. And the ones shown in magenta dots actually control the disease, and the one shown in green dots control the support device. And each of these are sample points along the latent trajectory. What we also did in this work was we curve fitted these sample points. So we did a Bezier curve interpolation across these sample points in the latent space. And those Bezier interpolations actually showed even more interesting results, which you can see in this animation. So let me try to play this. Give me a second. Yes, over here. So on the top, you can see an interpolation that was done using curve fitting for sample one, where we are controlling the disease. And at the bottom, we are doing these interpolations from Bezier curve using this approach that we talked about. There is another sample as well where we are controlling the same disease and where we are controlling similar devices. And to again refer to the fact that these latent points are from a curve-fitted approach. So we also showed it on ISIC and several other examples where we are able to control different attributes such as rulers, and it might not be very much visible. I don't know if the resolution is good enough, but I guess once I share the slide, you can see that the level of control that you observe over here is phenomenal in case of several of these attributes. The video is slightly long. It shows multitude of different attributes that you can control using this kind of approach. Now, the question arises, if I'm able to convince all of you that if we can control this, how is this useful? We can do synthetic data generation. So imagine situations where you have these large foundation models that could learn all these representations. Do we actually need real data? This might be a very ambiguous question, that do we actually need real data? Definitely yes, but there is a lot of uh, importance or a lot of positive things that we can get from these synthetic data, such as analyzing hidden relationships in data image attribute. We can create robust models. We could perform adversarial attacks, or we could even explore or understand causal nature, especially with drug discovery or pathologies in case of diseases that are rare, for which we don't have markers that we are associated or that we can associate with causal discovery. All those could be controlled if we have such good foundation models which understand the pathology and the semantic context. Finally, do we actually need real data? This is open for thoughts and discussion. Now, where to from here? So what I was able to show you is that we can have foundation models that can control quite a lot of things. We can have disentangled trajectories. We can even improve this foundation model using reinforcement learning. Just does the story end here? Not yet. So we have another paper at this DGM for MICAI, which will also be presented at this workshop, where we showed that these foundation models could be made even bigger. So this is the first time anyone has ever attempted to synthesize image at megapixel resolution for medical images. To the best of our knowledge so far, we haven't come across anyone who has tried to do so. And what I mean by megapixel scale is all those images that I showed you prior to this was 512 cross 512, which is already decently high resolution. In this paper, we push that even further. We go to 1024 cross 1024 and even beyond, which is 2048 cross 2048 using Stable Diffusion XL. This was done mostly by Zara and helped by Hujan and again supervised by Tal. So quick review of why do resolution matters in medical imaging. Over here, you can see a very clear graph. On x-axis, you have different resolutions. So starting from 64 cross 64 to 1024 cross 1024. On the left-hand side, you have AU-ROC of the classifier, and on the right-hand side, you have F1 scores. What you notice across several diseases, from cardiomegaly, lung opacity, edema, no finding, pneumothorax to pleural effusion, these classification accuracies and their F1 score actually improve if you have high resolution image. And this is done on one-on-one comparison. So it's the exactly same image that is sampled at low resolution and the exact same image that is at high resolution. So over here, this is just an intuition to show that resolution matters. Now, using the traditional approach, we actually showed why these resolution matters. So over here on the left-hand side, you have a classifier that says no pleural effusion. So essentially the decision of the classifier is wrong, as well as where they are focusing is also wrong. So again, same image, sampled at different resolutions. So from 64 to 128, 256, 512, 2024. And you can see that a traditional approach like GradCam is unable to even detect or diagnose. That's because just the model is unable to diagnose at this resolution. So incorrect classification leading to incorrect decision. Over here, we have the same image at high resolution, and now the same classifier is able to diagnose it correctly, as well as the gradients are localized at a good location. So that actually proves that we need high resolution image. So similar to Prism, but something more on top of that we have over here is we use larger embeddings, larger text embeddings such as OpenClip VIT or Clip VIT large. And these embeddings are fused with Stable Diffusion XL using cross-attention layers, and we use LoRa for fine-tuning this. This is different fine-tuning approach than what was suggested in Prism because there we literally fine-tuned all the components of unit, but such liberty is not available here because we have billions of parameter to fine-tune, specifically in this Stable Diffusion XL. So the output of this Stable Diffusion XL is 1024 cross 1024. We showed that using progressive scaling, this is mostly by hierarchical attention that we give to different layers on one on top of each other. We are able to successively scale these images from 1024 to 2048. Now, that's more about the background and how this was done. What do we get from here? These are the images that we were able to synthesize using Stable Diffusion XL. And now if you compare this to what I showed you at the beginning of the talk, you can see that, oh, these are extremely high resolution image, and also they require higher memory size. So you can see over here on the left-hand side, chest X-ray of a subject with pleural effusion, and you can see the level of details you can observe in these images. All these images are synthetically generated. None of them are real. And on the right-hand side, you have chest X-ray of a subject with cardiomegaly, and you can see that the fine details that can be observed by naked human eye is good enough at this resolution. So we are able to successively synthesize this at a megapixel scale. And just to convince you, here is a comparison with a real set of images. And you can see that using these boxes, we are able to show that the the properties that is associated with the disease or the pathologies that are associated with the disease can be observed very well in these synthetic images. However, we are restricted with time and amount of generation that we could do because these require more time, more compute resources. So so far we haven't done extensive analysis with these large foundation model. But what we showed that these synthetic image could be used or are very helpful in the context when you have low data. So if we just use 200 real samples and take these high resolution synthetic images, we are able to perform way better on a downstream classification task. And if you're interested, please do refer to the paper. Now, all that to show different directions of works that could be done. And finally, I'll talk about the last work that is also accepted at a different workshop, which is for agentic AI. And we put forward a paper that was called Aura, a multimodal medical agent for understanding, reasoning, and annotation. This was mostly done by my colleague Nima. And what we showed over here is all these tasks that we were performing so far were one component of medical analysis that could actually be deployed in clinic. What if we want to build a specialized tool that could perform all this at once, which is visual question answering, medical image segmentation, counterfactual image generation, and not only that, but do this in a cyclic manner, which is built on a React framework. I'm not sure if you're familiar with this. In summary, it's just a framework where the decision of a model can be re-evaluated by the agent itself and even made further better by doing this iterative process of generation and re-evaluation. So this architecture was called Aura and also uses Prism as well as other models under the hood. Here is a pipeline that shows how it works. So imagine user inputs a text prompt that remove pleural effusion and find visual explanation in this image, and an image was given. So step one is there is a thought process that is going behind this architecture, and this thought process are printed in green, and the output of the agent-based framework is printed in red. Unfortunately, I don't think I'll have time to go through each of these thought process or how these chain of thoughts are developed. But in summary, what's happening is this agent creates a thought process that, oh, I'm asked to remove pleural effusion. So first is localize, where is this pleural effusion happening? Second, if I'm able to localize it, what if I generate multiple counterfactual explanations, which is what if these patients were healthy? And it calls different modules. So not only Prism, but it also calls other modules that are deployed by other researchers across the world to see how does the model perform if other tools were used. And finally it's able to stitch together all those decisions and finally able to provide explanation as well as evaluation of that explanation using this entire framework. I'm skipping a lot of details here to respect the time. And another example was given over here that add a pacemaker to the chest. So far we were just looking at removal of devices. Here is an example which could be used more for study or stress testing. And what if you want to add something to the image? And again, the thought process is shown over here. Looking at the downstream tasks, so we talked a lot about Prism and some other image editing based method. This agent could also take those into analysis, and we showed that this you could specify bounding boxes that where do you need to make the change, and it's able to understand that context, evaluates its decision, and then improve the performance or generate something that shows semantic similarity between the synthesized medical image and what was instructed in the text. And such a method where this method is combined on top of a pre-existing method such as Prism or RADEDIT, you can see that the structural similarity or some of the metric where we show that counterfactual prediction gain, those are actually good. So in terms of the classification or in terms of the metric, you can see that Aura plus Prism is actually helpful, which proves this point of using an agent or a self evaluation based method is very useful in performing these tasks. So I hope I was able to provide some insights into how foundation models can be leveraged. in across variety of different tasks, and how could they be useful in promoting medical image analysis for an actual clinical deployment. A huge thanks to all the sponsors for this work, and thank you all for your attention. Merci beaucoup.